In this video, I want to give an overview of the scope of the lectures and an overview of linear hydroelasticity, applications of linear hydroelasticity, the components involved in linear hydroelasticity, which will then lead to the topics that we cover in the course. So again, this is only going to be restricted to linear hydroelasticity, specifically application to ocean engineering structures. The theory that I'm going to go over, I need to go over basic theories in structural mechanics, especially related to modeling of the structure, because that's very much key to a successful hydroelastic analysis. I need to review some basic concepts in structural dynamics and, of course, in hydrodynamics. That's going to focus on linear potential flow. As I mentioned in the previous video, most implementations of linear hydroelasticity use linear potential theory. And then I'm going to give an example application, as I mentioned again in the previous video. I'm going to work in detail an example of hydroelastic analysis starting from beginning to end. So that'll be a step-by-step demo, and I will be using HydranXR. Again, as I mentioned in the previous video, the steps will be the same no matter what code you use. You have to do the same, go through the same basic steps. All right, so hydroelasticity refers to the coupled dynamic response of a flexible structure in a fluid. The fluid is usually water, but it could be another liquid. But in our case, it's going to be water because we're focusing on ocean engineering applications. And the two domains need to be coupled in the sense that the fluid flow is influenced by the structural deformations, and the structural deformation is, of course, influenced by the fluid. In hydroelasticity, the response of the two domains is determined simultaneously. Rigid body hydrodynamics, it can be viewed as a subset of hydroelasticity, and what I mean by that will become clear later on. Counterexamples would be, for example, structures that are transparent, quote unquote, where the fluid is not really affected by the structure so much, and that, for example, is where Morrison's equation can be used. Another counterexample where it is a rigid immovable structure. When do we need hydroelasticity? Again, we need it when the structure influences the fluid flow. Otherwise, Morrison's equation or similar would be applicable. Again, we would need it when structural deformations are not small relative to the rigid body deformations regarding the fluid response. Otherwise, you can use rigid body hydrodynamics, which is well known for floaters. If it's not floating, then all movement is going to be elastic or deformational movement, and you would need hydroelasticity. Even if hydroelasticity is not per se required, there may be an advantage to using it because the structural forces and stresses are determined automatically as part of the analysis. This is as compared to what's traditionally done for rigid body hydrodynamics, which is broken down into a two-step process where the rigid body motions are determined. For example, motions is resulting from waves. And then the resulting pressures are applied to a structural model to obtain the forces and stresses. And these are typically applied statically. Now the components, as I mentioned, involve structural mechanics. Typically, it's going to involve a detailed global structural model. The modeler is going to need to understand the assumptions and practice in the finite element structural modeling. Finite elements is almost always used for the structure, for practical structures. Some background in structural dynamics is needed. And in hydrodynamics, of course, we need to be familiar with the assumptions, limitations, and modeling of the hydrodynamic theory that is being used. And coupling, that's the big issue. There are different numerical models are used for the fluid and the structure, and so we need to couple them somehow. And one needs to understand how they're being coupled and the limitations of the coupling methodology. So I want to go over some example applications for which hydroelasticity could be applied. Very large floating structures, or VLFS, is one class of structure that would typically require hydroelasticity. Mobile offshore base became popular about 20 years ago when the U.S. Navy investigated this application. What's shown here is a schematic of the J. Ray McDermott concept from that time. It's a structure that's 1,500 meters long and formed by coupling a large but somewhat traditional semi-submersible modules. For this particular application, the finite element model that was used was shown below here. We can see clearly the finite element models for each of the semi-submersibles, and involve 6,800 nodes and 13,600 shell elements. The modules were connected using quote-unquote hinge connectors. This is the panel model, which is different. This is the fluid mesh panel model. It involved 8,000 panels for the wetted surface only. And this shows some deformational motions. And I give here a reference for a journal publication that involved this application. You can also find these references on the website. The U.S. Navy did some model tests to validate the hydroelastic analyses, and this is a picture of a single module that was involved in those model tests. We'll come back to that when we talk about modeling. Another application is pontoon type VLFS. Somewhat typical of this application would be this ISSC VLFS benchmark. Again, it's documented in this in the reference cited below. This pontoon type VLFSs are essentially large floating barges, potentially rectangular hull shape. The finite element model for this involved over 19,000 shell elements. Another model that can be used is an isotropic flat plate, and this is all covered in this journal publication below. Floating offshore wind turbines is another application that's very popular these days. Again, an application here. The one that's shown here is discussed in the reference cited below. And the interest in offshore wind, and especially in deep water, this is a big application of where hydroelasticity is being used these days. This is an example of a jack-up structure with floating with the legs raised, again oriented more towards the larger structures in the typical floating or the typical drilling jack-up. Ocean thermal energy conversion is another potential application because it involves a very, very large diameter cold water pipe. Typically the structure on top probably could be considered rigid. It's certainly in this analysis, it's discussed in this reference, it was considered rigid, but then hydroelasticity was used for the pipe. So in this application, this so-called cold water pipe, it brings cold water up from deep water, and because of the volumes involved, it's a relatively large diameter, in this case almost 3 meter diameter and 1,000 meters long. Other applications are floating fish farms, and I give some citations, some URLs for applications that demonstrate these. Floating bridges or submerged floating tunnels. This is a Norwegian website where they're looking at solutions to cross fjords. Floating ice sheets, floating solar farms. This was an application that is in China. And hydroelasticity of ships, of course, is a more traditional one, I would say, and give a reference website for discussion there. So I want to talk a little bit about the distinctions between linear versus nonlinear hydroelasticity. So in linear hydroelasticity, we're limited to linear elastic material behavior. We're limited to quote-unquote small displacements, and that is a code word for linear kinematics. Typically what we were referring to there then is the small angles where the sines and cosines can be represented by either the angle for sine or 1 for cosine. Of course, we're also limited to a linear fluid model, and as I mentioned, most often the linear potential flow is used. The flow is typically inviscid fluid, and the flow is irrotational, and we use a frequency domain solution for the most part. In nonlinear hydroelasticity, we can accommodate large displacements for the structure, and we're going to be using a Lagrangian formulation almost invariably for that. We can include material nonlinearity. It doesn't need to be materially nonlinear to be nonlinear hydroelastic. We could have elastic behavior as well. And then typically, and what usually drives the requirement for nonlinear hydroelasticity is we need a nonlinear fluid model. And there we typically use an Eulerian formulation. So we're typically using a Lagrangian formulation for the structure and an Eulerian formulation for the fluid. CFD solvers are typically used for this. And of course, then it's got to be in the time domain. The big challenge there is the coupling between the Lagrangian structural mesh and the Eulerian fluid mesh. Our next topic is going to be an overview of some basic concepts of rigid floating structures, and that'll be in the next video. If you're coming at this from a naval architecture background, then you might want to skip that video. This covers some very basic concepts that are necessary, and I cover it for people coming at hydroelasticity from a non-naval architecture background.